Hi everybody, Mr. Zilipitz here. Mini lesson. Triangles make 180 degrees. When two angles form a straight line, like over here, that's 180 degrees. So triangles are 180 degrees. A straight line, half a circle, is 180 degrees. Circles are 360, triangles are 180. When you put a triangle inside a circle, that's 180, and there's 360 on the outside. So the edges of the triangle have three corners. In each one of those, let's say they're all 60, create a 120-degree arc. So if you put an angle on the edge of a circle, it'll make an arc that's twice as big as the angle. It's pretty amazing. Another thing, points, one letter, capital letter. Lines, two letters, capital letters, or one lowercase cursive letter. So you could have line AB, BA, or call it line L. Line segments, two letters, always. They are reversible. AB is the same as BA. It's just a little piece of a line. Array starts at one endpoint and then goes on forever. So when you do the endpoint, so ray AB starts at A and B falls somewhere on the ray. So array can only have one name if there's only two letters, but if there's multiple letters on the ray, you always start with the endpoint, which sounds funny, start at the end point, because everybody has to know where it starts, and then pick any letter along the way. So it might be AB, AC, AD, welcome to the dogs in the background. What are you doing, Bronco? Yes, 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 hi, hi, hi. One of the other things we've done, we've talked about planes. A plane is a flat surface. So think about the flat surface behind me. Pretend it goes on forever. Anything on that plane is on the board or on that wall. On the ceiling is another plane. When two planes meet, like in the corner here, they meet in a line. Planes go on forever, they're imaginary, but pretend they're like walls that go on forever. So if the wall in the corner, the side wall and the back wall meet, they meet in a line. A line intersects a plane in a point. So if I put this through my hand through the floor, it intersects in a point. Love that background noise. Bronco, Bronco, Bronco. So let's see, what else have we done? Parallel lines. When two parallel lines are crossed by a line, that's called parallel lines cut by a transversal. A transversal cuts the parallel lines into repeated patterns. The cool part is that when two lines cross, notice how the angle above my arms and below my arms is the same, and the angle to the left and to the right is the same. Pretend these were all 90 degrees. If they were all 90 degrees, 90, 90, 90, 90 is 360. Well, what if I shrink this in a little bit? Now I have two wider angles on the sides and two more narrow angles on the inside. So let's pretend where my head is 60 degrees. That means over here is 120, because 60 plus 120 is 180. And down here is another 60, because 120 plus 60 is 180. And then this 60 plus this 120 is also 180. And so all the way around, you have these angles that are next to each other that make 180, next to each other that make 180, next to each other, like here and here make 180, here and here make 180, and here make 180. And the whole thing makes 360. The angles across from each other are called vertical angles. Picture it this way, my head and below, vertical angles. But these and these are also vertical angles. Now, parallel lines form four kinds of angle pairs that we talk about. Alternate interior, alternate exterior, corresponding, and consecutive interior, or otherwise known as same side interior. Let me erase my toy boats, and I'll show you briefly. We've reviewed this in class many times. It's up to you to learn the vocabulary. but having at least a basic model can help you see what's going on, okay? So let's pretend that this is 60 degrees. This is a good model to draw for yourself every single time you need to do these problems, so that when people put algebra in it, you know what you're looking at. Because there are many places where the angles are the same, all the little angles are 60s, and all the big angles are 120s. And so we have various kinds of angle pairs. You can watch a video about this, you can read about it, you'll see notes in the resource list, you'll see notes at the top of this chapter, everywhere in the world, okay? So we have alternate interior, alternate interior, alternate exterior, alternate exterior. Notice exterior to the parallel lines. Then we have corresponding. There are 4 pairs of corresponding angles. They are the angles that are on the same side of the transversal, but one is inside and one is outside. So somebody came up with a name for it called corresponding angles. Notice how these two 120s are corresponding, just like these two 60s are corresponding. These two 120s are corresponding. These two 60s are corresponding. And so you have alternate exterior, alternate exterior, alternate interior, alternate interior, corresponding, 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 corresponding. And then the coup de grace are the ones that form a letter C that add up to 180 degrees. Notice these angles right here add up to 180 degrees. They have to. And those are called consecutive interiors because they follow each other. And they're also called same side interior because they're on the same side of the transversal. Transversal means cut across. They're on the same side of the transversal and they're interior and they're supplementary. So often teachers will teach it this way and say that same side interiors are supplementary. So that's parallel lines. That's what we've basically done so far this year. Oh, another thing we've done is the angle addition postulate. Little plus little equals big. The line segment addition postulate. Little line segment plus little line segment equals big line segment. So we have little plus little angle plus little angle equals big angle. Little plus little equals big. If you have a midpoint, it bisects a line segment, cuts it into 2 equal parts. So if I say M is the midpoint, you go, boop, these 2 are equal. If I say I have an angle bisector, it bisects the angle into 2 equal angles. So this angle would have a ray going through the middle that would make the top angle equal the bottom angle. Isosceles triangles have 2 equal sides and 2 equal angles. A scalene triangle has no equal sides and no equal angles. Isosceles has 2 equal sides and 2 equal angles. And an equilateral triangle has 3 equal sides and 3 equal angles. You use that to solve anything algebraic. So you learn concepts in geometry so that you can do algebraic things and also start to understand the world around you. Okay. What else can I tell you? Okay, so right triangles. When you have a right triangle, you know that you have a 90-degree angle, and one of the angles is 90, and that's the only 90 you can have, otherwise you'd have more than 180. So the other 2 angles also add up to 90. That's very helpful. So if you're missing one of the little angles, you just make the 2 of them add up to 90 instead of having to do the whole 180. The other thing is you could have an isosceles right triangle, which means you have a 90 and 2 equal angles, which means the other 2 angles, when you split the 90, is 45, 45. So you'll often hear me talk about a 45, 45, 90 right triangle. 45, 45, 90. What's cool about those is they're all the same shape. They're all the same shape. Any 2 triangles that have the same angles are the same shape, but they might be a different size. So one might be an enlargement of another one, but often you talk first in geometry, you talk about congruent things. Then you talk about similar things. Congruent means equal. Similar means you have to set up a proportion, which means cross-multiplying. So first we talk about congruent things, setting them equal to each other. Then we talk about proportionality, or A is to B is C is to D, that kind of things. Like if everything here goes 5, 8, that goes 10, 16, that goes 20, 24, whatever you want to call it. So triangles, the exterior angle theorem. The exterior angle theorem says this. When you have two angles next to each other, they make 180. When you have a triangle, it makes 180. And if you have a triangle that's 180 degrees, let's say this angle is 60 degrees. If this angle is 60, these two add up to 120. So if this little angle is 60, these two angles add up to 120. Keep that in your head, okay? Keep the 120 in your head. Put it over here on the shelf. Now, if this little angle is 60 degrees, if this is 60, this is also 120. So this plus this is 180, and this plus this is 180. So therefore, this is the same as this. So this 120 plus the 60 is 180, and these two angles plus the 60 is 180. So we simultaneously, isn't that fortunate the way our universe works, is that these two angles add up to this outside angle. The sum of the remote interior angles equals the exterior angle. And the great part is that's just a shortcut. 95% of the time you don't need to know it because you can work your way around the triangle to find what you need. Okay? So if you know these two angles, then you know the third angle in the triangle, then you know the thing on the outside. Because two triangles plus this makes 180, and then this plus this is 180. So you can follow your way around and go, okay, these make 100, so this is 80, so the thing on the other side of it is 100. And you go, oh, that's right. This outside is the same as the sum of these two because I have a 180 inside and a 180 going in and out of the triangle. The last thing I'll tell you is something that's coming up, and that's simplifying square roots. They show up in right triangles, so we learn and relearn how to simplify square roots or simplify radicals or simplify roots. Square roots can be turned into decimals, but that's for people who like to work. So most of the time, we turn things into simplified square roots. And the way you do that is the easiest way. You need to watch this video again. Take your number, make a factor tree. Write out the factor tree. Look for pairs, because something times itself means something squared. So if I ask you what's the square root of 2 times 2, that means what's the square root of 4, which is 2. Because the square root means what number times itself gives you that number. Now this is going to sound silly. What number times itself gives you 2 times 2? What number times itself gives you 5 times 5? What number times itself gives you 7 times 7? What number times itself gives you 3 times 3? So what's the square root of 3 times 3? 3. What's the square root of 9? 3. What's the square root of 25? 5. What's the square root of 5 times 5? 5. Each time you're asking yourself, what number times itself gives you that number? When you're simplifying square roots, the thing is, if something doesn't have a pair, then that's an ugly number that is best served by staying underneath the square root. So your answer to, for instance, the square root of 8, 8 is 4 times 2, which is 2 times 2 times 2. So I write down the square root of 2 times 2 times 2. Oh, there's a pair of 2's. What's the square root of 4? 2. What's left under the house? A square root of 2. And you might say, what's the square root of 2, Mr. Z? And I would tell you, I don't know and I don't care. It's the square root of 2. That is the simplest form of 1.414 blah, 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 blah. It goes on forever, doesn't stop, doesn't repeat. So if you round it, your answer is going to be different than somebody else's because there's no standard of rounding. People round different ways. And the less you round until you're ready to finally finish building your space rocket, the more likely it is for the rocket to stay in the air. Okay? So mathematicians and scientists don't turn radicals, square roots, into anything else until the very end of their calculations, which is often a really, really, really long time when you're building something. Okay? We do that because of special right triangles. Special right triangles is different from Pythagorean triples. Right triangles that have whole number sides are called Pythagorean triples, named after Pythagoras, even though he's not the first one to discover the Pythagorean theorem. Some of your basics are 3, 4, 5, 5, 12, 13, and 8, 15, 17. If you can remember those three or have them written down in front of you, it can save you a lot of work. The other kind that we talk about are special right triangles. Special right triangles are 45, 45, 90 triangles because they have a special pattern that makes them easier to work with, and 30, 60, 90 right triangles. And a 30, 60, 90 triangle started out as a full 60, 60, 60 triangle. So picture this having all equal sides. If this is 8, the bottom is 8. And if you cut the triangle in half, you have an 8 right here and a 4 right here. And then if you use the Pythagorean theorem, you'll get this ugly decimal, but it looks very cute if you leave it as a square root form using the Pythagorean theorem. A squared plus b squared is c squared. So if this is 8 and this is 4 times the square root of 3. If this is 2, this is 4, this is 2 times the square root of 3. If this is 5, this is 2.5, or 5 over 2. This is 5 radical 2 over 2. If this is 12, this is 6, this is 6 square root of 3. The diagonal side is always the longest, and it'll always be double the tiny side. Now, square root of 3 is less than 2 because it's like 1.85. So this is 2 times 1, this is 2 times 2, this is 2 times the square root of 3. So here we go. 5, 10, 5 square root of 3. Isosceles right triangles are even easier. So picture it, these two are the same. So if this is the same, so I have basically my hand in my hand, right? My hand in my hand, my hand in my hand. So if I make an isosceles right triangle, that means I have a 45, 45, 90 right triangle. And if you do the math with the Pythagorean theorem, it'll look like this. 1, 1, 1 times the square root of 2 is the hypotenuse. 2, 2, 2 square root of 2. 3, 3, 3 square root of 2. 5, 5, 5 square root of 2. 10, 10, 10 square root of 2. So the hypotenuse in a 45, 45, 90 triangle is always the leg times the square root of 2. And the legs are the same. And the pattern, because of the Pythagorean theorem, turns out the same every single time because they're all the same shape. And as you make the hypotenuse bigger, the legs get bigger. If you make the legs bigger, the hypotenuse gets bigger. But it's still the exact same shape, just being stretched out. So it goes 5, 5, 5 square root of 2. 6, 6, 6 square root of 2. Now, if the diagonal is 6 times the square root of 2, well, that means the original little leg was 6 because it became 6 times the square root of 2. 6 becomes 6 times the square root of 2. So if the multiplier wasn't there, in other words, you divide by it, the multiplier is divided out, you get back to the original. So 5 square root of 2 started out as a 5 because the pattern is 5 times the square root of 2. When the numbers get ugly, that's when we learn something else called rationalization. Rationalization is when you have a square root in the bottom of a fraction. There's a rule in math speak that says you're not allowed to have a negative exponent left in your expression because it doesn't tell what's really going on if you're dealing with exponents. And there's this other thing called rationalizing. You're not allowed to have a square root in the bottom because, believe it or not, a square root is actually an exponent. It actually is an exponent of 1/2. You don't have to understand why yet, but it is. That's why you're not allowed to have a square root in the bottom, number 1. The other thing is, the main reason is that it's actually a negative exponent because it's in the bottom. So 1 over the square root of 2 is really 2 to the negative 1/2 because it's in the bottom and it's a square root. And so mathematicians say, we can't have a square root in the bottom. It's too ugly. It takes more work. So the square root of 1 over the square root of 2. Right? Picture it. 1 over the square root of 2. You have to make the square root disappear. If you square the square root or multiply it by itself, you'll have the square root of 2 times the square root of 2 is the square root of 4, which is 2. The square root of 3 times the square root of 3 equals the square root of 9, which is 3. So if you multiply by the top and the bottom by that, whatever that square root is, it'll make the square root disappear from the bottom and it will appear at the top. Because you can't just randomly multiply the bottom of a fraction by something. So if I have 1 over the square root of 2, I multiply the bottom and the top by the same thing. What do I multiply by? Whatever's in the bottom. Square root of 2 has got to disappear. So if I square it, I have to multiply the top and the bottom by the same thing like I've always done. Like what if it said 1 over 2 and I want it over 10? I do 2 times 5, 1 times 5. If I want it over 12, 2 times 6, 1 times 6. So if you multiply the bottom by square root of 2, you multiply the top by the square root of 2. These numbers will look ugly, but I just multiply the top and the bottom by the exact same thing. And the new concept is multiplying the bottom by a square root. That multiplying something times itself is actually really easy. The square root of 2 times the square root of 2 is the square root of 4, which is 2. So the square root of 3 times the square root of 3 is 3. Square root of 5 times the square root of 5 is 5. However, my brain doesn't like to skip the middle step. The square root of 5 times the square root of 5 is the square root of 25, which is 5. Some people jump right from square root of 5 times the square root of 5 is 5 to 5. Square root of 7 times square root of 7 is 7. Or in their head, they go, that's the square root of 49, that's 7. Or what number times itself gives you 7 times 7? 7. What was the purpose of multiplying by the square root? To get rid of the square root. So even if you're having a hard time following what's going on, all you need to remember is that you multiply the top and the bottom by the same ugly number. If you multiply the top and the bottom by the same ugly number, the bottom becomes pretty and the top will be transformed. So whatever's on the top is just going to get brought along for the ride. So it might look like this. 5 over the square root of 2 times is 5 times the square root of 2 over 2. Now I know that sounds really hard to follow, but if you actually write down what I said, it'll make a lot more sense. So learn to rationalize. Make sure you know everything I talked about in this video. So if you have missed classes for any reason, up through September 18th, we didn't talk about transformations again. Transformations. Here's the quick. Slide, translation. Flip, reflection. Okay? Different things happen. You flip over the x-axis, it becomes upside down. You flip over the y-axis, goes like that. You flip over here, x becomes y, y becomes x. If you flip over here, both the x and the y coordinates flip. So rotations, the x and the y change places, and one of them becomes positive, one of them becomes negative. There's a video for you to watch in the resource section that shows how to do transformations. And you could also see how to use Desmos. Okay, now this was a very long video. It's going to take up a lot of space on my computer, but I'm going to see if I can upload it into my drive and share with you forever. So welcome to geometry. This is basically the first 8 weeks of geometry. Peace.